Hey fellow nerds. Today we are going to discuss the basics of BJT amplifiers. We'll start by forming an idea on how to build a BJT amplifier, then move on to biasing, transconductance, small signal hybrid pi model of a BJT, and early effect. First, let us revise what we have already learned. Assume we have an input signal that looks like this. Using clipper circuits, we were able to make all these outputs. We can say that a clipper circuit removes or clips the portions of a signal above or below a certain voltage level, effectively shaping the waveform by limiting its amplitude. Using a clamper circuit, we were able to get all these outputs. Basically, we can say that a clamper circuit shifts a signal vertically by adding a DC level to its waveform, ensuring the signal's peaks are clamped to a desired reference voltage. Assume I'm taking the same sinusoidal input and I want my output to look like this. Basically, what is happening is the entire waveform is multiplied by a constant. V output is a constant multiplied by V input. For example, if this point is V naught, then this will be K times V naught. Or if this point is V1, then this point will be K times V1. This process is called amplification, and a system that does this can be called an amplifier. If you give an input like this to an amplifier, you will get an output that looks like this. The output will have a higher amplitude when compared with the input. Since the amplitude of the signal gets increased, we call the process amplification, and the system that does it is called an amplifier. Now we have to design a system that actually does this. First, let's make an idea on how this can be possible. Assume we have something like this inside the amplifier. We are giving our input over here and it creates a voltage V1 over here. Inside the amplifier, we have a dependent current source. What does the current source depend on? It depends on the voltage that we give over here, V1. Let us assume that the current I given by the dependent current source is directly proportional to the voltage that we get over here, V1. That is, I is a constant multiplied by V1. Again, I is the current that flows through this circuit. So I is the current that flows through the resistor RL and it is flowing in this direction. We know current flows from the positive potential to the negative potential. So the resistor RL must be having positive potential here and negative potential here because the current is flowing in this direction. Using Ohm's law, we can write the voltage across RL. V is equal to IRL. Positive potential is here, negative potential is here. Now, if you take a look at the output, we are taking the positive of the output from the negative of the potential across RL. Negative of the output is taken from the positive potential across the RL. That means output is going to be negative of whatever is the potential drop we have across RL. So we can write V output is minus IRL. But I is K times V1. So here we can write V output is minus KV1 RL. Now here in the circuit you can see that V1 is basically V input itself. That means instead of V1 here we can write V input. That gives us this. V output is minus KV input RL, or we can write V output is minus KRL multiplied by V input. Basically, the output is input multiplied by something. This is amplification. So from this idea, I can say that all we need to create an amplifier circuit is a voltage dependent current source. I think we already have a device that acts as a voltage dependent current source. It is the bipolar junction transistor in its active mode. We saw that in the previous video. So, we are going to use a bipolar junction transistor in its active mode as a voltage dependent current source so we can make an amplifier. Let's see how to do that. What we want is a current source over here that should depend on the voltage that is given over here. Let us add a BJT to the circuit and see if it works like that. The input is applied across the base emitter junction, and the collector current will be flowing in this direction. So basically the collector current will be flowing through the resistor like this. We know how the collector current is dependent on the base emitter voltage. It is Is e raised to VBE by VT. Obviously, IC over here depends on whatever is the voltage we are giving across these 2 points. So our idea has to work. Whatever we have inside the box should work as an amplifier and amplify our input signal. Let us draw the circuit in a different way. All the connections are the same. I have only made it look better. Here you can see IC is the current that flows through the load resistor in this direction. Current flows from the positive potential to the negative potential. So the resistor must have positive potential here and negative potential here. But obviously for the output, positive is taken from the negative, negative is taken from the positive. So V output is going to be negative of the potential drop across the load resistor. So we get V output is negative of RL IC. But IC is IS e raised to VBE by VT. So we can write V output is minus RL IS e raised to VBE by VT. Now let us try giving some numbers. My input is a mic. It is giving a sinusoidal signal as an input. Amplitude of my sinusoidal input signal is 10 millivolt. Let us take the saturation current to be 5 times 10 raised to minus 16 ampere. We know output is negative of RLIC and IC is ISE raised to VBE by VT. VBE is taken from the input. So the maximum value of the input is going to be 10 millivolt. Assume we want an output whose amplitude is 100 millivolt. That is, we want the input waveform to be multiplied by 10. Let us calculate how much will be the value of RL in that case. Since V output is minus RL ISE raised to VBE by VT, to get the value of RL, we can write V output divided by ISE raised to VBE by VT. V output will be 100 millivolt. IS is 5 times 10 raised to minus 16 ampere. VBE is 10 millivolt. VT is the thermal voltage 26 millivolt. If you give the numbers, this is what you get. We need a resistor of resistance almost 4.26 times 10 raised to 16 ohm. But this is too high. Is there something we can do so that we can use a resistor with a reasonable value? Let me try this. I will take the same circuit and modify it like this. Along with my sinusoidal input of amplitude 10 millivolt, I have also given a DC supply 750 millivolt. So the total voltage that we get between the base emitter junction is going to be 750 plus 10. Let us again assume the output voltage is supposed to be 100 millivolt. Let us try to find the value of RL. The only difference is VBE here will be 750 plus 10, that is 760 millivolt. This is what we get. It is approximately 40.39 ohm, which is obviously a reasonable value. What we had to do is add an extra DC supply over here. Now, just this much is not enough. We said a bipolar junction transistor that is in active mode acts as a voltage dependent current source. So we have to make sure the BJT we have is in active mode. That means its base emitter junction should be forward biased and the collector base junction should be reverse biased. We have given 750 millivolt positive here and negative here. The input will also be given as positive here and negative here. So we have already made sure the base emitter junction is forward biased. We have to make sure the collector base junction is reverse biased. For that, we will add a cell over here in this direction. Earlier, when we added a cell like this, we used to call it VCE because it was directly connected between the collector and the emitter. But right now, we have a load resistor over here. So the entire DC voltage is not between the collector and emitter. Some of it will be dropped across the resistor also. So now we are going to call it VCC. It is the voltage we are supplying to the collector terminal. CC is for common collector. The method of adding a DC voltage between the base and emitter is called biasing. Along with that, we also have to add VCC over here. It keeps the transistor in active region so that it works as a voltage dependent current source. Determine the output voltage if Is is 5 times 10 raised to minus 16 ampere. We have our amplifier circuit over here. Input as a DC voltage 750 millivolt. VCC is 3 volt. Load resistor is 1 kilo ohm. First, let's try to find the collector current. IC is Is e raised to minus VBE by VT. Value of Is is given in the question, VBE is given in the question, VT is the thermal voltage, it is 26 millivolt. So let us give all the values. If you calculate this, you will get 1.69 milliamperes. So this is the current that is flowing through the resistor in this direction. And we know current always flows from the positive potential to the negative potential. So the load resistance must have positive potential here and negative potential here. Now consider this loop. I am going to apply KVL. I'll start from this point and go clockwise. As I go from here, I have a 3 volt from negative to positive. The next thing I see is the potential across the load resistor, but it is from positive to negative. So I will write minus ICRL. As I go on, I have output voltage again from positive to negative. So I am going to write minus V output. This is equal to 0. That gives me V output is 3 minus ICRL or VCC minus ICRL. We already found IC is 1.69 milliamperes. RL is given, it is 1 kilo ohm. Let's give the values. V output is 3 minus 1.69 multiplied by 10 raised to minus 3 multiplied by 10 raised to 3. This is equal to 1.31 volt. Our input was 750 millivolt. The output we are getting is 1.31 volt. We could say that the output is 1.75 times the input. Let us continue our discussion on biasing. Value of RL becomes reasonable after biasing. Why? Because biasing provides proper voltage and current so that the transistor can amplify. What happens is this. When we give a DC supply over here, that will already give a good amount of collector current. For example, in the previous problem, when we give 750 millivolt, we got a collector current of 1.69 milliampere even before we gave the input. The problem we faced before giving biasing is that the collector current was really less. Because if the collector current is really less, to get the required output, RL should be really high. Because V output is minus RL IC. If IC is small, that means RL should be too high. So by biasing the circuit, we are making sure that the collector current is high enough that we can use a reasonable value for load resistor. Now, we know how collector current changes with base emitter voltage. It increases exponentially with increase in base emitter voltage. We plotted it like this before. In this case, I have taken a base emitter voltage of 750 millivolt. Let me mark it on the graph. I can find the collector current from the graph like this. From the previous problem, we found that if the VBE voltage is 750 millivolt, collector current we get is 1.69 milliampere, or approximately we can write 1.7 milliampere. We call this the operating point of the transistor. Operating point is the bias values we have chosen for VBE and IC. For example, here we took VBE to be 750 millivolt and that gave us IC to be 1.7 milliampere. Let us compare two different operating points. In the first case, I have taken VBE to be 750 millivolt and I got IC to be 1.7 milliampere. In the second case, I have taken 780 millivolt to be VBE and I got IC to be 5.3 milliampere. Consider the first case. I want to increase the input voltage by 10 volt from 750 to 760. Let us see how much the current will change. When voltage changed by this much, current changed by this much. If we calculate it mathematically, we get the change in current is 780 microamperes. That is, the difference between the current over here and 1.7 milliamperes is just 780 microamperes. Let us do the same thing for the second transistor. Its operating point is 780 millivolt and 5.3 milliampere. I'm going to increase VBE by 10 millivolt. Let us see how much the current will change. You can see that for the same change in voltage, change in current is much high. If we calculate mathematically, the change in current is going to be 1.7 milliampere. Let us compare the two transistors. For the first one, whose operating point is 750 millivolt and 1.7 milliampere, a change of 10 millivolt in the base emitter voltage created only 780 microamperes change in the current. We can say that this transistor is less sensitive to change in VBE. The second transistor has its operating point at 780 millivolt and 5.3 milliampere. For a change of 10 millivolt in VBE, it creates a change in current that is equal to 1.7 milliampere. So obviously this is more sensitive. This is the conclusion we can make. A bipolar junction transistor can act as a voltage dependent current source. That is, collector current IC changes with respect to VBE. The most important point is the operating point or the biasing determines how the transistor responds. The next concept we have to learn is transconductance. We have IC as IS e raised to VBE by VT. We established IC changes with respect to VBE. Now we have to find out how much does IC change with respect to VBE. For that, let us calculate the rate of change of collector current with respect to the base emitter voltage, dIC by dVBE. We have to differentiate IC with respect to VBE. That is d by dVBE of IS e raised to VBE by VT. Is a constant, let's take it out of the differentiation. Now all we have to differentiate is an exponential function which is pretty easy. Derivative of e raised to VBE by VT with respect to VBE is e raised to VBE by VT divided by VT. So we get this. dIC by dVBE is Is by VT e raised to VBE by VT. But Is e raised to VBE by VT is IC. So we can write this is just IC by VT. So we get dIC by dVBE is IC by VT. We know IC is a current, VBE is a voltage. According to Ohm's law, V is equal to IR. So V by I should have dimensions of resistance. That means I by V should have dimensions of conductance. Here we have current by voltage, so this quantity should be a conductance. But there is a slight difference. Usually when we write V is equal to IR, V is the voltage across the resistance, I is the current that is flowing through the same resistance. But over here, IC is the collector current or the output current. VBE is the base emitter voltage or the input voltage. Because of that reason, we call this transconductance or transfer conductance. It is called transfer conductance because it quantifies the transfer of control from an input voltage VBE to a corresponding change in the output current IC. It is denoted as GM. G denotes the reciprocal of resistance, that is conductance, and M is for mutual because transconductance can also be called mutual conductance. Let us put this in a box. We can see that Gm is directly proportional to IC because Vt is the thermal voltage and it is a constant. So if we plot the relationship between Gm and IC, this is what we get. The slope of the graph is going to be 1 by thermal voltage. Again, we know IC is Is e raised to VBE by Vt. So we can write the expression for Gm like this also. Is by Vt e raised to VBE by Vt. That means Gm has an exponential relation with VBE. So if we plot the relation between Gm and VBE on a graph, this is what we get. Let us again take the two transistors we compared earlier. The first one has an operating point 750 millivolt and 1.7 milliampere. Second one has 780 millivolt and 5.3 milliampere. Transconductance is IC divided by VT. For the first one, IC is 1.7 milliampere. So if we calculate transconductance, we get 0.078 Siemens. Siemens is the unit for conductance. For the second one, IC is 5.3 milliampere. If we calculate the transconductance, we get 0.17 Siemens. Obviously, the second one has higher transconductance than the first one. We have already seen the first one is less sensitive and the second one is more sensitive to any change that is happening in the input voltage. Let us now try to create a model for bipolar junction transistor just like we did for a diode before. For amplification, we use bipolar junction transistor in active mode. So we'll be using a bipolar junction transistor in active mode for our model. Let us take the circuit symbol of a transistor. I have also marked IC. IB will be flowing in this direction. And we know IB is IC divided by beta, beta being the current gain of the transistor. We know base is P doped, emitter is N doped. Since the transistor is in active region, it is forward biased. So basically between base and emitter, we have a diode that is forward biased. And some current IB which is equal to IC by beta will be flowing through it. So we can model that part like this. We have the base over here, we have the emitter over here. Between base and emitter, I have connected a diode. Potential across the diode is VBE. Current that will be flowing through it is IB, which is equal to IC by beta. Let's again go back to the circuit symbol. We have emitter current in this direction. I have shown that in the model also. So this is what is happening here. Base current flows in this direction. Collector current is also coming in this direction. They together flow through the emitter, creating the emitter current. Emitter current is the sum of base current and collector current. So we can consider that from the collector to the emitter, a current IC is flowing. This current depends on how much voltage we apply between the base and emitter. So I am going to show this in the model as a dependent current source. Like this, the current source gives the current IC which is equal to Is e raised to VBE by Vt. You can see that IC is flowing in this direction, IB is flowing in this direction, and together they make up IE. These are the mathematical relations we can use. IC is Is e raised to VBE by Vt. IB or the base current is IC divided by beta. So we can write IC by beta e raised to VBE by Vt. IE is the sum of IC and IB, but since IB is really small, we can say it is approximately equal to IC. Also from the first equation, we can write VBE is VT log of IC by IS. Let's take an example. This is my circuit. I have my transistor over here. I have given V0 over here and VCE between the collector and emitter. Why have I called this V0 and not VBE? Because it is not directly connected between base and emitter. We have an emitter resistor over here. Let us see how we can draw the model of this circuit. First, we'll take the model of a bipolar junction transistor. Now, at the emitter, we have a resistor. Let us add it in the model. Between the base and this point, we have V0. Let us add that also. Also, between the collector and this point, we have VCC. Let us also add that. This is the circuit model we can use for analysis. Here, IE is flowing in this direction. But we know current always flows from the positive potential to the negative potential. So across RE, we should have positive potential here and negative here. We can apply KVL in this loop. If I start from this point and go clockwise, V0 is from negative to positive, VBE is from positive to negative. Voltage across RE is also from positive to negative. So I can write V0 is VBE plus VRE. But according to Ohm's law, voltage across RE will be IERE. So this is what I get. V0 is VBE plus IERL. But if IB is considered really small, IE will be approximately equal to IC. So I can write V0 is approximately equal to VBE plus ICRL. Also, we know VBE is VT log of IC by IS. We can even use that. That will give us V0 is VT log of IC by IS plus ICRL. This way we can do the analysis and find whatever we want. Now, consider that we have a transistor that is properly biased. I have given a DC input V0 over here. That gives me a collector current IC0. I have also supplied VCC to the collector. Let us now give a sinusoidal input to this circuit. Along with V0, I also have V input now. V input is sinusoidal. In that case, the potential we get between the base and emitter VBE will be V input plus V0. When the input changes, obviously the output will change. So when V input is added, the collector current will change. It will not be IC0 anymore. Let us call the new collector current IC. Assume that our input signal looks like this. Now, if I plot VBE, it will look like this. VBE is V input plus V0. V input is sinusoidal, V0 is just a DC value. So the input waveform will be shifted by V0 units. So this is the circuit we have and this is the voltage we give at the base emitter junction. Let us take the IC versus VBE graph of this transistor. First, let us mark the operating point of the transistor. Here the transistor was biased by adding V0 over here. And V0 gave us a current of IC0 at the collector. So the operating point will be V0 and IC0. So we can say that before we applied the input voltage, VBE was V0 and the collector current was IC0. Now, once we apply V input, this is the voltage that we get at the base emitter junction. It is not constantly at V0, it is sinusoidally varying about V0. Let us show that in the graph. VBE is not constantly at V0 anymore, it is varying like this. We can say that VBE is sinusoidally varying between these 2 points. That means IC will be varying between the corresponding 2 points here and here. This is the conclusion we can make. The input voltage is disturbing our operating point. How much does it disturb? That depends on the amplitude of the signal. Assume we have a large signal and a small signal. If the signal is large, you can see the operating point will be changed from this point to this point. But if it is small, the disturbance is also small. We can conclude that if the signal is small, meaning its amplitude is small, then it disturbs the operating point only by a small amount. Let's consider a signal is large. Our input is a sinusoidal waveform Vm sin omega t. Its amplitude is Vm, and consider Vm is an arbitrarily large value. Since we have V0 and V input between the base and emitter, we can write VBE is equal to V0 plus Vm sin omega t. Now, if we want to find out the collector current, this is the expression that we use. I is e raised to V0 plus Vm sin omega t divided by Vt. We have a sine function in the exponent. This will make the math difficult and the analysis will become complicated. Let us now assume that our signal is small. That means Vm is an arbitrarily small number. Now, we should have a measure of what is small and what is large, right? How do I know which signal is small and which signal is large? To understand that, let us take a look at this equation again. IC is Is e raised to VBE by Vt. We have VBE by Vt over here. VBE is compared with Vt, which is the thermal voltage. So if VBE is a fraction of Vt, we can consider it to be small. Otherwise, we have to take it as a large signal. So for now, let us assume that Vm is very much less than Vt, so that we can consider the input to be small. Since Vm is very much smaller than Vt, if we take Vm sin omega t divided by Vt, it is going to be very much less than 1. Let us bring this equation again. We have Is multiplied by e to the power V0 plus Vm sin omega t divided by Vt. V0 plus Vm sin omega t divided by Vt can be written as V0 by Vt plus Vm sin omega t by Vt. So we get this. Here we have e raised to V0 by Vt plus Vn sin omega t by Vt. This can be written as e raised to V0 by Vt multiplied by e raised to Vm sin omega t by Vt. Now consider this part, e raised to Vm sin omega t divided by Vt. We already found Vm sin omega t by Vt is very much less than 1. We can use the relation e raised to x is approximately equal to 1 plus x if x is very much less than 1. Here the power of e is Vm sin omega t by Vt, which is very much less than 1. So we can approximate this part to 1 plus Vm sin omega t by Vt. If we do that, this is what we get. Now over here we have Is e raised to V0 by Vt. We know Ic is Is e raised to VBE by Vt. Here instead of VBE we have V0. So this is the collector current that we get when the base emitter voltage is V0. But we have already given a name to it. It is IC0. So we can replace this part by IC0. So IC is IC0 multiplied by 1 plus Vm sin omega t by Vt. You can see that by assuming the signal is small, the math is getting simpler. Let us open the bracket. We get IC0 plus IC0 by Vt Vm sin omega t. IC0 is a DC value, it is a constant. IC0 by Vt Vm sin omega t is sinusoidally varying. So we can say the collector current is sinusoidally varying. Again, we can see that Vm sin omega t is our input. It is V in. Now, what is IC0 divided by Vt? It is the transconductance Gm. So finally we can write IC is IC0 plus Gm V input. Let's put it in a box. Let us go back and take a look at these graphs again. Here we have taken the large signal, so the operating point varies from this point to this point. The relation between IC and VBE between these 2 points is exponential. If we plot IC like this, you can see that the upper half is not symmetrical to the lower half. That means IC is not going to be sinusoidal. But if we consider the signal to be small like this, these 2 points will be close to our actual operating point. So we can approximate the graph between these 2 points is almost a straight line. Over here, if we project the IC, we can see that IC might actually become sinusoidal. So when we assume the signal is small, we are basically approximating the graph to be a straight line. We take IC to be proportional to VBE rather than the exponential relation they actually have. So this is what we got. We gave V0 to bias the transistor and we gave a small signal as an input. This made VBE equal to V input plus V0. And the output we got is IC0 plus GMV input. But if you remember, when we simply biased the transistor with V0, the output was equal to IC0. Now we added another input and we got another output GMV input. So we can say IC0 is the output for V0 and GMV input is the output for V input. So technically these two inputs are not interfering with each other. That means we can consider this circuit to be a combination of these two circuits. Here the input is V0 and the output is IC0. Here the input is V input, which is a small signal, and the output we get is GMV input. If we combine them together, we get our actual circuit over here. Input is V input plus V0 and output is IC, which is IC0 plus GMV input. Let us now try to draw circuit models for these two. Consider the bias part first. I'll take the transistor model we made earlier. V0 is connected between the base and emitter. Let us show that in the model also. We also have to show VCE connected between the collector and emitter. This is the circuit model. Let us now move on to the small signal one. I'll again take the model of a transistor. Between base and emitter, I have to add the small signal as input. Collector and emitter are shorted. Let us show that on the circuit model also. Now, this is not entirely correct. When the signal is small, we found IC becomes GMV input. IC is proportional to the input voltage. The current that flows through here is IB. And IB is equal to IC divided by beta. Beta is current gain, it is a constant. So since IC is proportional to V input, IB will also be proportional to V input. V input is the voltage that we apply between these 2 points. IB is the current that flows between these 2 points. So if IB is directly proportional to V input, it is more accurate for us to connect a resistor over here instead of a diode. Using Ohm's law, we can write V input is equal to IB multiplied by the resistance of the resistor, which means V input will be directly proportional to IB. So when the signal is small, it is better to model the base emitter junction using a resistor like this. So when the signal is large, we can use this model of the bipolar junction transistor, and when the signal is small, we can use this one. So this is the large signal model and this is the small signal model. In this particular case, potential that drops across the resistor over here will be equal to V input. But in a different circuit, it could be different. So in general, let us take the voltage across the resistor to be V pi and let us call the resistor R pi. But that must mean instead of GMV in over here, we'll have to write GMV pi. because the collector current depends on whatever is the final voltage between the base and emitter. Now, this is called the small signal hybrid pi model of a BJT. Let's do some math now. We know base current IB is the collector current divided by beta, where beta is the current gain. But here IC is GMV pi, so we can write IB is GMV pi divided by beta. Again, IB is the current that flows through this resistor. Potential across it is V pi and the resistance is R pi. So IB has to be V pi divided by R pi. We can cancel V pi here and V pi here. That gives us R pi is equal to beta by GM. Let's put the relation in a box. Let us take an example. We have a circuit over here and we have to draw its small signal hybrid pi model. First, let us start with the small signal hybrid pi model of a BJT. At the emitter, we have a resistor. Let us show it in the circuit model. Now, between the base and this point, here we have V input and the bias V naught. But we are drawing the small signal hybrid pi model, so we do not have to consider V naught. It is the bias. So we will put V input between those 2 points. Now, between the collector and this point, we have VCE also. But it is also a large signal and we don't have to consider it in the small signal model. Without VCE, these 2 points will be shorted. So that is how we are going to show it in the circuit model. Let us see the next one. We have a circuit and we have to draw the small signal hybrid pi model. We will start with the small signal hybrid pi model of a BJT. Since we are drawing the small signal hybrid pi model, we can obviously ignore V0 and VCE. In that case, between base and emitter, we have V input over here. Let us show that in the circuit model. Since we are also ignoring VCE, between the collector and emitter, we have a resistor RC. Let us show that also in the circuit model. Let's solve a problem now. Determine the small signal parameters of Q1 if V input is 0. Q1 is the name of the transistor in the circuit. And when we say small signal parameters, we mean R pi and GM. Because those are the two values we need to draw the small signal model of a transistor. It is also given IS, the saturation current is 3 times 10 raised to minus 16 ampere. Beta, the current gain is 100. Q1 operates in the active mode. First, let's try to find out the collector current IC. IC is IS e raised to VBE by VT. Taking V input to be 0, we can consider VBE to be 800 millivolt. VT is 26 millivolt. So we get 3 times 10 raised to minus 16 multiplied by e raised to 800 divided by 26. And this comes out to be 6.92 milliamperes. Now let's find the transconductance GM. GM is IC divided by VT. IC is 6.92 milliamperes and VT is 26 millivolt. This comes out to be 1 by 3.75 ohm. I have put ohm in the denominator. Instead of that, you can also write 1 by 3.75 Siemens. We also need to find out R pi. R pi is beta divided by GM. Beta is 100, GM is 1 by 3.75 ohm. So we get R pi is 375 ohm. Since we got GM and R pi, let us draw the small signal hybrid pi model of this transistor. R pi over here will have a value 375 ohm and GM over here will have a value 1 by 3.75. Since this is a small signal model, we can ignore the 800 millivolt bias voltage and 1.8 volt VCE. So between base and emitter, we'll only have the input voltage and the collector and emitter will be shorted. Let us now move on to another important concept, early effect. To understand early effect, I have again taken the schematic diagram of a transistor. Earlier, we said IC is given by this equation. Is e raised to VBE by VT. There is only VBE in the equation. VCE is not there. And we said IC is independent of VCE. We even plotted a graph that looked like this. This shows IC is completely independent of VCE. But there is a problem with this idea. We know VCE provides a reverse bias to this junction. That means when VCE increases, this junction will become more reverse biased. And that will make the width of the depletion region increase. If the width of the depletion region increases, that means width of the base decreases. That means when an electron in the N plus region reaches the base, it will be easier for it to reach the depletion region and be swept to the N region by the electric field in the depletion region, which basically means the collector current will increase. Let us write this down. When VCE increases, width of the depletion layer increases. That means base width decreases. That means it is easier for an electron to cross the base, therefore collector current increases. This means the graph between IC and VCE is not going to be exactly a horizontal line like this. IC in fact does depend on VCE a little bit. So the graph will actually look like this. This phenomenon is called early effect. Early is the name of the scientist who first described it. Now, if we consider early effect, we obviously will have to modify this equation because this equation does not contain VCE in it. This is how we modify it. We'll have to multiply whatever we have right now with 1 plus VCE divided by VA. This is the new equation for collector current. Let us put it in a box. Here, VA is the early voltage. Now, before we explain what is VA, we have to understand one more thing. We saw when VCE increases, width of the depletion layer also increases. But this will make the base width decrease. We call this the base width modulation. The early voltage VA is not an actual voltage that is dropped anywhere in the circuit. It is a hypothetical voltage that quantizes the base width modulation. For example, assume VA is really small. That means VCE by VA will be really large, which makes IC very much dependent on VCE. And that gives us base width modulation is really high. On the other hand, if VA is really large, then VCE by VA will be a really small number. We can approximate it to 0 and this term simply becomes 1. Then we can say IC is not that much dependent on VCE and therefore base width modulation is really less. So this is what we can conclude. A larger early voltage indicates less modulation of the base width, and a smaller early voltage implies significant modulation. Therefore, when early voltage is infinite, VCE by VA will become almost equal to 0 and we'll get IC to be IS e raised to VBE by VT. In that case, early effect can be ignored and we can consider this to be an ideal current source. Let us now try to figure out how we can show early effect in the small signal model of a BJT. Assume VCE changes by delta V and that creates a change in the collector current delta IC. VCE became VCE plus delta V and that made the collector current IC plus delta IC. Let us take the equation that relates IC and VCE. Here VCE becomes VCE plus delta V and because of that IC becomes IC plus delta IC. So I will replace IC over here with IC plus delta IC and VCE over here with VCE plus delta V. This is what I get. We have VCE plus delta V by VA here. This can be written as VCE by VA plus delta V by VA. Let us split the entire equation into two like this. I have I is e raised to VBE by VT multiplied by 1 plus VCE by VA over here. And I is e raised to VBE by VT multiplied by delta V by VA over here. Now, what we have here is IC. But this entire thing is IC plus delta IC. That means this must be delta IC. So delta IC is IS e raised to VBE by VT multiplied by delta V by VA. We need to find out how much does a change in VCE affect the collector current. So let us write delta V divided by delta IC. From the above equation, we can write it like this. It is VA divided by IS e raised to VBE by VT. Let us make an approximation now. Over here in this equation, we have VCE divided by VA. Now, in most cases, VCE is really small when compared with VA. So, VCE by VA is a really small value, which means we can approximate IC to be simply IS e raised to VBE by VT. And we have IS e raised to VBE by VT over here. So, we can say this is approximately equal to VA divided by IC. Now, delta V is a small change in voltage that is happening at the output. Delta IC is a small change in the current that is also happening at the output. So when we take delta V by delta IC, we should be getting an output resistance. We can call this R naught. The value of R naught will be VA divided by IC. Here the change in voltage is really small. The change in current due to that is also really small, which means we have to include this in our small signal hybrid pi model. Let us see how we can do it. First, I will take the small signal hybrid pi model of a transistor. The small change in voltage is happening between the collector and the emitter. The small change in current because of that is also happening between the collector and the emitter. So to show that, we can add R naught between the collector and emitter like this. Now, if there is any change in the voltage between the collector and emitter, because of R naught, obviously there will be a change in the current that is flowing through here, which is the collector current. We have perfectly modeled it. So when you include early effect, this is how the small signal hybrid pi model of a BJT looks like. We'll have to add an output resistance R naught, which is equal to VA by IC. Let us do something. I have made a circuit over here. The BJT is biased with V naught. I have also given a small signal input, V input. VCC is given at the collector. And I have also added a resistor over here at the collector. I am calling it RC. Finally, I am taking my output from the collector. I want to start by drawing the small signal model. First, I will take the small signal hybrid pi model of a BJT. V0 can be ignored, VCC can be ignored. So between the base and emitter, I will have my input voltage. Between collector and emitter, I will have my RC. I want to calculate V output. It is obviously taken across RC. According to Ohm's law, potential drop on RC will be current through it multiplied by RC. So I will take I to be the current that is flowing through RC. Consider this node. Let us apply KCL. I is flowing out of the node. GMV pi is also flowing out of the node. So we can write GMV pi plus I is equal to 0, which means I is simply minus GMV pi. So we can write V output is IRC or minus GMV pi RC. But from here we can see V pi is actually V input. So let us replace V pi by V input. We get V output is minus GM V input RC. Here, Gm is the transconductance. It depends on the operating point of the transistor, which is determined by V naught over here. V input is the small signal input that we are giving to the transistor. RC is the resistor we have connected between the collector and the emitter. We can see V output is directly dependent on RC. So my question is, will increasing RC increase V output without any limit? If I make RC infinitely high, does that mean I get an infinitely high output no matter what is the input I'm giving? Will I get an infinite amplification? Sounds like the idea is great, but we just learned about early effect. If you consider early effect, you will have to add another resistor between collector and emitter, that is R naught. Now, between collector and emitter, we have RC and R naught, and they are both in parallel. So we can write the equivalent resistance between collector and emitter is going to be RC parallel to R naught. That is RC R naught divided by RC plus R naught. Let us divide the numerator and the denominator by RC. Then this will become R naught divided by 1 plus R naught divided by RC. My question was, will increasing RC infinitely increase the V output without limit? Let us see what happens if we make RC infinite. If RC becomes infinite, R naught divided by RC will become 0. That means our R equivalent will become just R naught divided by 1 plus 0 or R naught. No matter how much you increase RC, R naught is going to limit the effective resistance you're getting between collector and emitter. So if RC is really high, the combination of RC and R naught in parallel will be equivalent to just R naught. We can remove RC in the circuit model. In that case, V output will become minus GM V input R naught. This is what we can conclude. Early effect limits the amplification. I have one more question. We have learned that if early voltage is infinite, that means we can ignore the early effect. We can remove R naught. In that case, we will only have RC over here in the output. Then V output will become minus GMV in RC. Now, if I increase RC infinitely, will I get infinite output? Well, the answer is no. Early effect is not the only thing that limits us from increasing RC to infinite and get an infinite amplification. There are other reasons also, but that is thought for another time. Let us move on to the next concept, saturation mode. Assume we have a bipolar junction transistor. We have applied VBE across the base emitter junction, VCE across the collector emitter junction. To use a BJT as an amplifier, we want it to be in the active mode. That means base emitter junction should be forward biased and collector base junction should be reverse biased. By applying proper VBE, we have made sure the base emitter junction is forward biased. VCE is applied between collector and emitter. So we have to make sure that the collector base junction is reverse biased. Collector is N doped, base is P doped. So to make the junction reverse biased, we should give positive potential here and negative potential here. Or technically, the potential that the collector gets should be greater than the potential that base gets. VC should be greater than VB, or VC minus VB should be greater than 0. But VC minus VB is VCB. So VCB should be greater than 0. Now VCB can be written as VCE minus VBE. That means VCE minus VBE should be greater than 0 so that the collector base junction is reverse biased. Or we can write VCE should be greater than VBE. So what we can say from here is this. If VCE is less than VBE, that means the transistor is no longer in active mode. The circuit will not act as a voltage dependent current source anymore. When VCE is less than VBE, we say the transistor is in saturation mode. Let us write this down. When VCE is smaller than VBE, collector base junction becomes forward biased. That means the transistor is no more in forward active region. We say the transistor is in saturation mode. So to avoid saturation, we have to make sure VCE is greater than VBE. In case our device is silicon based, VBE will be 0.7 volt. Let us see how to show this in the IC versus VCE graph. At first, we had the graph look like this. Then we learned about early effect and we made the graph look like this. Now we saw that if VCE is less than VBE, that means the transistor is no more in active mode and it will not act as a voltage dependent current source. Instead, IC will decrease like this and go to 0. So, an accurate IC versus VCE graph of a bipolar junction transistor looks like this. We did all of our discussion by taking an NPN bipolar junction transistor. Emitter was heavily N doped, base was P doped, and collector was also N doped. I had said in the previous video that we can also make a PNP transistor like this. Emitter will be heavily P doped, base will be lightly N doped, and collector will be lightly P doped. To make the base emitter junction forward biased, we connect the negative terminal of the cell to the base, that is N doped, and positive terminal to the emitter, that is heavily P doped. Even VCE is connected the same way. Negative terminal is connected to the collector and positive terminal is connected to the emitter. Here we have lots of extra holes in the emitter region. Since base emitter junction is forward biased, they will cross the junction and reach base. And they will immediately reach the depletion region because base is really thin. And they will be pushed to the collector region by the strong electric field in the depletion layer. Since holes are flowing in this direction, collector current will also be in the same direction like this. That means emitter current is in this direction. Since base has extra electrons, some of the holes will recombine with the electrons. We have connected negative terminal of the cell to the base, so extra electrons might come from the external circuit to the base in this direction, making a current flow in the opposite direction. This is our base current. Basically, the directions of all the terminal currents are opposite. The circuit symbol of a PNP transistor is like this. Since the emitter current is going in, we have shown that over here in the circuit symbol also. Let us try to derive the condition to keep this in the forward active region. We want the collector base junction to be reverse biased. But collector is P doped and the base is N doped. So base should have a higher potential than the collector so that the junction is reverse biased. VB should be greater than VC, or we can say VB minus VC should be greater than 0. But VB minus VC is VBC. This should be greater than 0. Now, VBC can be written as VBE minus VCE. That gives us VBE minus VCE should be greater than 0. Or we can write VCE should be less than VBE. Here VBE will be negative 0.7. So VCE should be less than minus 0.7. That means VCE should be a higher negative value than 0.7. Or instead we can write VEC should be greater than 0.7 volt. Let us also see the small signal hybrid pi model of a PNP transistor. These are the differences. Obviously, collector current is in the opposite direction. So here GMV pi will be in the opposite direction. IB flows in this direction. That means it flows through the resistor like this. And we know current flows from the positive potential to the negative potential. So V pi will have positive potential here, negative here. So that's all about it for today. See you in the next video. And don't forget to subscribe.